Okay, section 3.8 is about continuity and end behavior. When we talk about a function being continuous, it means that it's going to move smoothly, and for every value of x, we're going to have an output for y. And there's not going to be jumps or anything like that. So the definition officially is a function is continuous if it is defined at that point, defined meaning that it has a y value at that point, and it passes through that point without a break. So we're not going to break and move elsewhere on that point. But obviously then discontinuous means if there's a break or a gap through that point. We all know what the graph that, or we should, by the way. If we don't, we need to evaluate, or we need to look at your parent graphs. But we should know that the graph of the function 1 over x has a vertical and a horizontal vertical asymptote uh, along the y-axis and a horizontal asymptote along the x-axis, and we should know that it looks something like this. This is what we call infinite discontinuity. No matter what, there is no value for x equal to be 0. In fact, x can never be 0 because that would make this function undefined, right? So x can never be 0. Therefore, we have what's called an infinite discontinuity. It'll never it doesn't come here and it doesn't pick up elsewhere. It just all of a sudden almost starts a new graph on the other side. That is what's called infinite discontinuity. Let me scroll down. Jump discontinuity would be something like this. I'll give you an example, and I pulled it up on a graph here. This is an example, absolute value of 2x divided by x. Here's what that graph looks like, and let me zoom in a little bit farther. But what this graph looks like, from the left here, this blue line is what that is. From the left here, all right, that is going along, it's going along a straight line, straight line, straight line, but then all of a sudden when we get y equal to, or x equal to 0, this line goes from way down here and it jumps actually up to here, and then it continues and it's all positive. The y values are positive, which makes sense. If we plugged a negative value in, like -5, the absolute value of -5 is 5, right? Divided by -5 is a -1. And in fact, no matter what value we're going to pick on the negative side, it's always going to be -1. That's what that graph is showing, because we're dividing by that negative. If we any number that we pick, like in a positive, like say +4, the absolute value of 4 is 4, divided by 4 is 1, is a +1. So that's going to end up here. But when we have 0, 0 obviously makes the function undefined, but we notice that there's a jump there. This thing gets all the way to 0, but then it jumps up here from the negative up to the positive. That's what we call a jump discontinuity. That's one example of that. Point discontinuity, we've talked about this already. We've talked about holes before. We know that we can go ahead and, this is a difference perfect square, so we could write this as, x plus 1 and x minus 1, right? And then on the bottom, it also has an x plus 1, and this cancels out right here. And in fact, if we graph this thing, it would look like the equation x minus 1, but it would have what we call a hole at -1. Well, because -1 makes the original function undefined. So that hole at -1, we would go, let's see, it looked like y equals x minus 1, but we'd say because of this graph right here, we're going to have a hole at x equal to be -1 because of that canceling out right there. So if we go down 1 and then our slope is up 1 over 1, right? Like that, and then down 1 over 1, there's that hole right there. And we all know what this looks like. And then down 1 over 1, up 1 over 1. That is what's called point discontinuity. Everything is continuous except for that point right there, and just has that point right there that's not continuous, has that hole, that jump. Okay, so that's what we're talking about when we talk about continuity and discontinuity. We're going to use your calculator to describe the end behavior of a function. I'm going to show you this function. I'm going to pull it up on my calculator over here, and I'm going to go ahead and type it in here. Let's see. Let's get rid of this guy and let's type that in. 5x cubed plus 4x squared minus 2x plus 4. And let's graph that guy. the end behavior is what is it doing as x is getting closer and closer and closer and closer to infinity. So as x keeps getting bigger and bigger and bigger. So as we go out here, what is the y? What are the y values doing? Well, notice that as we keep getting, this is x equals -7, and we're already down here to 420. You know, -420. You notice that this function is going to negative infinity as x goes to negative infinity. So to answer that question, we would say as x approaches negative infinity, y approaches negative infinity. And then as x approaches positive infinity, which means as x gets bigger and bigger over here to the right, what is the y value doing? The y's, they're getting bigger and bigger in the positive direction. See, look, we're already up to 420 again, and we're only at x equal to be 4, right? So if they wanted to know the end behavior of this graph, we would answer that question as x approaches infinity, or as x approaches negative infinity. We saw as x got negative, y approached negative infinity. It got bigger and bigger negative. Then we'd say as x approached positive infinity, as it got bigger, y would approach positive infinity because that was way up on the positive side. And then our notes say here, look for the end behavior of an even function. So let's go ahead and let's just make up some crazy even function. We're going to say 10x to the 6th power plus 8x to the 5th power minus 3x to the 4th power plus 2x cubed plus 10x squared plus x plus 5. And I mean, it's just some ridiculous number, but it's an even function. The leading coefficient here has an even coefficient right here, all right? Or not an even coefficient, the coefficient would be 10. An even degree, all right? So from this leading coefficient, we're going to be able to tell what this graph is going to be doing. It's going to have an even at the end. It's going to look like a parabola. So everything that has a leading thing with the leading, can't think of the word right now, but the leading term, the one with the biggest degree, there we go, leading term, the one with the biggest degree is going to tell us what our graph is going to look like. This is an even degree, which means it's going to be in the shape of a parabola, just like x squared and x to the 4th. They're all in the shape of a parabola. So every even function is going to have the same end behavior, which means as x gets negative, so as we're going over here, as x keeps getting negative, what are the y values doing? Well, the y values keep going on up. It's in the shape of a parabola, right? So what we would have written is, we would say as x approaches negative infinity, so as x gets bigger and bigger to the negative, what is y doing? Well, y is approaching positive infinity. In fact, we're all the way up to 2,500. And the same side, we got to look on the other side. As x goes to positive infinity, so as x gets bigger and bigger and bigger this way, what is y doing? Well, y is going to go to positive infinity. So in an even function, in an even function, you're always going to have this. In an odd function, you're always going to have something like this. Except for if we mess with it, maybe we put a negative out in front, that might flip the graph around. But for this even function, we're going to have a parabola. Unless we have a negative in front, then it might change the parabola down like that. But if we're looking at the end behavior of our graph that we had, we would say as x approaches negative infinity, I made that an 8, negative infinity, y approached positive infinity. And as x approached infinity, so as x got bigger and bigger on the positive side, y approached positive infinity as well. So that's what end behavior is. We're looking at the very end of the graph. Why is that going to help us? When we get to curve sketching, we'll know where we'll be able to start from the end, and then we'll find some critical points, and we'll basically be able to connect the dots. So we know maybe it's an even function. It'll start way at the top there. Maybe we had to have a critical point right here where it's going to change to going from decreasing to increasing, and then it might change again, it might change again, change again. But anyway, we can graph crazy functions like that. So it might not be that crazy, so it looks like that shape, but you get the picture. So the last part is saying here, a function is increasing if and only if, the capital IFF means if and only if. And what that's saying, f of x1 has to be less than f of x2, is meaning like if I pick a point, so here's an increasing function like this. All right, if this point's y value is bigger than this point's y value, then it's increasing. Well, duh, we knew that, right? If it has a positive slope, it's going to be increasing. If it has a negative slope, it's decreasing. And I say that in this paragraph right here. It's easier way to tell whether it's decreasing. Just look at the slope of its tangent line. If the slope of its tangent line, which would be what we get from when we take the derivative, is positive during that interval, then the function is increasing. If the slope is negative, then it's decreasing. All right? So these last examples here, all right, we're going to graph and determine the intervals for which the function is increasing, decreasing. And I'm going to actually show you an easy way. We don't actually have to graph the thing. We know from end behavior, and we know from critical points where the stuff is going to change, all right, that we don't actually have to graph it. So if we were to look at this guy's slope, all right, this guy's slope, if we took the derivative of it, would be, what, negative 2x is all. If we found its critical points, we'd have a critical point at x equal to be 0, right? And we know from end behavior, look, this is going to be a parabola, but this negative sign means it's going to be something like this, turned upside down like that because of that negative sign. Well, look, if we pick a point to the left of our critical point, which is 0, like negative 1, pick negative 1 and let's put it into our derivative. So negative 2 times a negative 1. We get a positive slope, and that makes sense. Right here is x equals negative 1. My function is increasing here, all right? And my slope of my tangent line is positive. And in fact, that's got to stay the same throughout this whole thing unless there's a critical point. The only way it can change from increasing to decreasing is when there's a critical point. But we know that critical point isn't until 0. So in fact, we know from negative infinity, so like as x is really big over here, no matter what, as x is getting closer and closer to 0, so from negative infinity to 0, this thing is increasing. All right? Well, on the left or on the right side of this critical point, if we plugged in, say, positive 1, if I plugged a positive 1 into my derivative, which is negative 2x, I'd get negative 2, which is a negative slope, which means it's decreasing. And we know that that can't change unless we have a critical point. So from 0 to then infinity, my graph is decreasing. We're always going to have a negative slope. All right? All right, and then if we look at the graph 1 all over x, we already know what that graph looks like. We already know what the graph looks like here. And we'll draw a line like that. Determine the points in which it's increasing and decreasing. Well, as we go from infinity closer and closer to negative infinity closer and closer to 0, we see that that function is decreasing easily, all right? So it's decreasing from negative infinity to 0, it's decreasing. And then as we're going from left to right here, from 0 to positive infinity, it's also decreasing. And my computer's going crazy right now. So from 0 to infinity, it's also decreasing. And so they're decreasing in both cases in that one. All right. And one last case, find out where this guy is increasing and decreasing. Let's try to do it. Let's try to do it where we can. Let me pause. I'm going to pull up the graph for you in a second. I'll show you that way. Okay, I've pulled up the graph for you on this equation, our next example, and we're looking for the intervals for which it's increasing and decreasing. Well, this is actually kind of interesting. We pull up this graph, and we notice from as x approaches from negative infinity, it's increasing, 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 increasing until it gets to a point somewhere in here, and then all of a sudden it starts decreasing. Then it hits a point again, and it's going to start increasing again. Well, the thing about this is we're going to actually have to find it's where these intervals are, where it's decreasing inside here. And we'll pull that information that we used from that last section. We better find those critical points to tell where this thing is increasing and decreasing. To find those critical points, remember we're going to take its derivative. So we have 6x squared plus 16x plus 8, and we're going to set it equal to 0. Find its critical values. To find these guys' critical values, we have a trinomial here. We can either use a quadratic formula, or we can try to factor this thing. Let's try to factor it. I can take a 2 out of each of those guys, and I'll get 3x squared plus 8x plus 4, and that equals 0. To factor this guy, I have a coefficient out here that's bigger than 1. I know that something's going to have to multiply. If I multiply 3 and 4, I get 12. I need to figure out something that multiplies to be 12, add up to be 8. Signs have to be the same and both positive. 6 and 2, that'll fit the bill. So we'll have, let's see, 3x squared plus 6x plus 2x plus 4. I'm just factoring this thing, and maybe you guys have a different method of factoring. The quadratic formula always works. But all I did is I kept 3x squared and I kept 4. What I had to do is I defined something that multiplies to be 12, adds up to be 8, and then I just replaced that 8 with what multiplied to be 12 and added up to be 8 here. And then I'm going to group it and factor that thing out. So I'm going to group these guys together, and what can I pull out of that first? This first guy, I can pull a, let's see, I can pull a 3x out, and I'll be left over with x plus 2, and I can pull on the top here, I can pull a positive 2 out, and I'm left over with x plus 2, which is good, and that 2 is still out in the middle. Which is good because since these guys are the same, we know from grouping that then we can rewrite the stuff that's outside of the group. So 3x plus 2, we can write that together in a parentheses, and then we can write this x plus 2 together in a parentheses, and there we have it factored already for us with a 2 on the outside. So if we want to solve for critical points, we set each of these equal to 0. Well, obviously this 2 is going to go away. 2 equals 0, that's nothing. Set this equal to 0, we get 3x plus 2 equals 0, subtract our 2, divide by 3. We get x equals negative 2/3. And then we get x equals negative 2 for our critical points. And remember now, our function, when we looked at our graph, it was doing something like this, right? But in this middle part, it was decreasing for a little bit, okay? So we know that 2 is out here, obviously. By looking at the graph and comparing our critical points, we know from negative infinity to negative 2, up until it gets to negative 2, it's increasing. But then when it gets to this critical point, a critical point means that it's changing direction. So once it gets to this critical point, it's going to go from increasing to decreasing. So from negative 2 up until we get to the next critical point, which is negative 2/3, it is decreasing. So from negative 2 to negative 2/3, it is decreasing. And then obviously from our graph, then from negative 2/3 and on to infinity, it was increasing. And I'll pull that graph up and show you. So it's increasing. All right. And another way you guys could do it, we learned this in the last section. Pick a point to the left of x, left of negative 2, plug it into our derivative and see what it's doing. If it's a positive slope, then it's increasing. If it's a negative slope, it's decreasing. Pick a point on the other side, and we can tell from there whether it's increasing or decreasing. Let me pull up that this thing again, and look right there. We at x equal to negative, so there's negative 2 actually here. We found that to be a critical point, so we know that this graph's starting to decrease here at negative 2. And then at about negative 2/3, maybe right here, it stops, and it's going to start increasing again. So there we figured that out. I hope this helps. We'll see you in